Gauss studied curvature of surfaces, like two-dimensional surfaces, right? And he found that there's a way to intrinsically describe the curvature without stepping off the surface. Right? That was a new discovery. You don't have to be off the surface to know that a curvature exists and to describe it mathematically. And Riemann developed the idea of an intrinsically curved space, where you use the same kind of geometry, not for something that is a curved surface in some other space, but just a space by itself having the same kind of geometrical properties as, for example, a curved surface, the geometry on a curved surface, or the geometry of curvilinear coordinate lines. Comma r in a subscript means derivative with respect to r. We'll start out first with the simplest example of curvature, not space-time, but just a two-dimensional surface curved in like this. Gauss is the one who came up with the formula for the curvature of such a surface. And his formula, given a metric, two-dimensional metric, okay, you just have two terms, basically you can have two metric coefficients, A and B, because you have two dimensions. If you look at this metric over here, a two-dimensional metric, guys here, these are the metric coefficients. What appears, though, in the formula that Gauss used, he had the square roots of these things, the positive square roots. So you have, remember that a comma means a derivative, and the thing after the comma is the coordinate with respect to which you're taking the derivative. G, A, comma, B means take the thing in front of the dA square, that's GAA. Take the square root of it, the positive square root, that's GA. Take the derivative of that with respect to the coordinate B, divide by GB, and then take the derivative of that with respect to the B coordinate. Then you have the other term there, which has exactly the opposite, GB comma A over GA comma A. And this is the curvature. So what do you have? What kind of term? You have GA comma B over GB. GA comma B means GA, derivative with respect to B. B is a coordinate of one particular dimension. Okay? And that whole thing, you take the derivative of it with respect to the coordinate B. Plus the next term, and GB comma A over GA, derivative with respect to A. You have the metric coefficient of one dimension, take the derivative of it with respect to the coordinate of the other dimension, and divide it by the G of that dimension. Then take the derivative of that whole thing, again with respect to the coordinate of that dimension. Basically, again, the gammas are derivatives of the g's, and the curvatures have to be derivatives of that. It's how each of those metric coefficients change with respect to one or other of the other coordinates, normalized out by the g of the other coordinate. And that's exactly what these connections do. And the derivatives of that are the curvature. You can see kind of intuitively, in a sense, how that would take into account the curvature. Look at the right-hand side over here. I wrote r equals gamma prime plus gamma prime. Right? We expect curvatures should be connection derivatives, derivatives of connections. Right? That's basically what curvatures are, at least in two dimensions. So basically the form of it is gamma prime plus gamma prime. You have basically the derivative of this guy with respect to this guy, and derivative of this guy with respect to that guy.
You say the system was orthogonal, right?
Right.
So how do you have GA comma B? Is that
because you're not having, it's a curved metric, so you have functions in front of, you have, let's say, r squared d theta squared. So you're taking the derivative of r squared with respect to it.
Okay. Yeah.
So you're going to have a derivative of the g divided by another g, and then the derivative of that. So basically the form of it is gamma prime plus gamma prime. Those eta, those are just plus or minus signs. Two metric coefficients, A and B. And multiply the two of them. You have GA times GB, and take the inverse, and multiply that by this whole thing in the squiggly brackets. Now, what are the two terms in the squiggly brackets? Look at the square brackets within the squiggly bracket. Look at those two terms to see the symmetry. Okay? The things in the bracket, forget about the etas. It just gives you the sign. Can you see that you have A, B, B, B in one of them, and B, A in the other one? Okay? Switch over in the first term from A, change every A to B in the whole thing. What do you get? forget about the A, yeah, even A to A, leave those and then switch from A to B, like you did replace, global replace, A goes to B and B goes to A, what would happen?
It's the same.
It's exactly the same